Hello, and welcome to the first episode of the Software Carpentry lecture on the Unix Shell. In this episode, we'll explain what a shell is and why you might want to work as if the year was 1975. At a high level, computers really do four things. They run programs, they store data, they communicate with each other, and they interact with us. They can do the last of these in many different ways. For example, they can use telepathy, i.e. direct brain-computer links. This technology is still in its infancy, but I for one look forward to being assimilated as it matures. Another way to interact with computers is to talk to them. No, talk to them, not dock the pen. As you can tell, this technology is also still somewhat immature. What most of us use for interacting with computers is a WIMP interface: windows, icons, mice, and pointers. While these technologies didn't become widespread until the 1980s, the roots go back to Doug Engelbart's work in the 1960s, which you can see in what has been called the mother of all demos. Going back even further, the only way to interact with early computers was to rewire them. But in between, from the 1950s to the 1980s and into the present day, people have used a technology that's based on the old-fashioned typewriter, and that technology is what we're going to explore in this lecture. Now, when I say typewriter, what I actually mean is a line printer connected to a keyboard, like the DeckWriter LA36 shown here. These devices only allowed input and output of the letters, numbers, and punctuation found on a standard keyboard, so programming languages and interfaces had to be designed around that constraint. Although, if you were clever enough, you could find ways to do simple pictures using just those characters. This kind of interface is called a CLUI, or Command Line User Interface, to distinguish it from the GUIs, or graphical user interfaces, that most of us are now used to. Normally, a user starts a CLUI session by logging in with a user ID and a password. The user then types a command. The computer executes the command and prints its output. In the case of older terminals, literally printing the output onto paper a line at a time. The user then types another command, which the computer executes, displaying output, and so on until the user logs off and takes his or her roll of paper away to study. From this description, you'd think that the user was sending commands directly to the computer and that the computer was sending output directly to the user. In fact, there's a program in between called a command shell. What the user types goes into the shell, which figures out what commands to run and orders the computer to execute them. The computer then sends the output of those programs back to the shell, which takes care of displaying things to the user. A shell is just a program like any other. The only thing that's different about it is that its job is to run other programs rather than to do calculations itself. The most popular Unix shell is Bash, the Bourne Again shell. It's called that because it's derived from a shell written by Stephen Bourne. This is what passes for wit among programmers. Bash is the default shell on most modern implementations of Unix, and also comes with Cygwin, the Unix on Windows toolkit that we're using in this course. Using it, or any other shell, feels a lot more like programming than like using Windows and mice. Commands are terse, often only a couple of characters long, and their names are often cryptic. So why should you use it? There are two good reasons. First, many tools only have command line interfaces, or are easiest to use, particularly on remote machines, through the command line. Second, the shell allows you to combine existing tools in powerful ways to create new tools of your own with little or no programming. As we'll see later in this lecture, this lets you do a lot of work with just a few keystrokes, once you have paid the upfront cost of learning how the shell works and what its basic commands are. In the next episode, we'll take a look at how to find your way around files and directories using the shell. Hello, and welcome to the second episode of the Software Carpentry lecture on the Unix Shell. In this episode, we'll have a look at how files and directories are organized and how to navigate around them. As we said in the last episode, a computer has four main jobs: run programs, store data, communicate with other computers, and interact with us. One way the computer can interact with us is through a command shell. We type commands, the shell tells the computer to run programs on our behalf, and then the shell shows us the output from those programs. Some of the commands we will use most often are ones related to storing data on disk. The subsystem responsible for this is called the file system. It organizes our data into files, which hold information, and directories, which hold files or other directories. In the next few minutes, we'll see how we can use the shell to view what's in the file system. Or to be more precise, how we can use the shell to run other programs that will show us what's in the file system. Let's start by logging into the computer. Here, we're showing the shell's prompt in bold and explanatory text, like this message, in blue. Type our user ID, we'll show user input in green, and then our password. Most systems will print stars to obscure it, or nothing at all in case some evildoer is shoulder surfing behind us. Once we have logged in, we'll see a shell prompt, which is usually just a $sign, but which may show extra information like our user ID. The shell prompt is exactly like Python's triple greater than prompt. It signals that the shell is waiting for us to type something in. Type "Who am I?" followed by enter. This command prints out the ID of the current user, i.e., shows us who the shell thinks we are. When we enter it, the shell finds a program called "Who am I?", runs it, displays its output, and then displays a new prompt telling us that it's ready for more commands. Now that we know who we are, we can find out where we are using pwd, which stands for Print Working Directory. This is our current default directory, i.e., the directory the computer assumes we want to use unless we specify something else explicitly. The computer's response is /users/vlad. To understand what this means, let's have a look at how the file system as a whole is organized. At the very top of the file system is a directory called the root directory that holds everything else the computer is storing. When we want to refer to it, we just use a slash character. This is the leading slash in /users/vlad. Inside that directory, or underneath it if you're drawing a tree, are several other directories, such as bin, which is where some built-in programs are stored, data, users, where users' personal directories are located, temp, for temporary files that don't need to be stored long-term, and so on. We know that our current working directory, /users/vlad, is stored inside /users because /users is the first part of its name. Similarly, we know that /users is stored inside the root directory / because its name begins with /. Underneath /users, we find one directory for each user with an account on this machine. The mummy's files are stored in /users/imhotep, the wolfman's in /users/larry, and ours in /users/vlad, which is why Vlad is the last part of the directory's name. Notice, by the way, that there are two meanings for the / character. When it appears at the front of a file or directory name, it refers to the root directory. When it appears inside a name, it's just a separator. Let's see what's inside Vlad's home directory by running ls, which stands for listing. It's not a particularly memorable name, but as we'll see, many others are unfortunately even more cryptic. ls prints the names of all the files and directories in the current directory in alphabetical order, arranged neatly into columns. To make its output more comprehensible, we can give it the argument or flag -f. This tells ls to add a trailing slash to the names of directories. As you can see, there are 7 of these. The names without slashes, notes.txt, pizza.cfg, and solar.pdf, are plain old files. Here's that output again with a picture of what it's showing us. You may have noticed that the file's names are all something.something. By convention, the second part, called the file name extension, indicates what type of data the file holds. .txt signals a plain text file, .pdf indicates a PDF document, .cfg is a configuration file full of parameters for some program or other, and so on. However, this is only a convention and not a guarantee. Files contain bytes, nothing more. It's up to us and our programs to interpret those bytes according to the rules for PDF documents, images, and so on. Now let's run the command ls-f data, which tells ls to give us a listing of what's in our data directory. The output shows us that there are 4 text files and 2 directories. This hierarchical organization helps us keep our work organized. Notice while we're here how we spelled the directory name data. Since it doesn't begin with a slash, it's a relative path, i.e., it's interpreted relative to the current working directory. If we run ls-f/data, we get a different answer because /data is an absolute path. The leading slash tells the computer to follow the path from the root of the file system, so it always refers to exactly one directory, no matter where we are when we run the command. What if we want to change our current working directory? pwd shows us that we're still in users vlad, and ls without any arguments shows us its contents. We can use cd followed by a directory name to change our working directory. cd stands for change directory, which is a bit misleading. The command doesn't change the directory, it changes the shell's idea of what directory we are in. cd doesn't print anything, but if we run pwd after it, we can see that we are now in users vlad data. If we run ls without arguments now, it lists the contents of users vlad data because that's where we are now. Okay, we can go down the directory tree. How do we go up? If we're still in users vlad data, we can use cd ... to go up one level. ... is a special directory name meaning the directory containing this one, or more succinctly, the parent of the current directory. Sure enough, if we run pwd after running cd ... we're back in users vlad. The special directory ... doesn't usually show up when we run ls. If we add the -a flag, though, it will be displayed. -a stands for show all. It forces ls to show us directory names that begin with dot, such as ... which, if we're in users vlad, points to the users directory. We also see another special directory that's just called dot, which is the directory we're currently in. It may seem redundant to have a name for where we are, but we'll see some uses for it in later episodes. Everything we have seen so far works on Unix and its descendants, such as Linux and Mac OS X. Things are a bit different on Windows. Here's a typical directory path on a Windows 7 machine. The first part, C:, is a drive letter. This notation dates back to the days of floppy drives, and even today, each drive is a completely separate file system. Instead of a /, Windows uses / to separate the names in a path. This causes headaches because Unix uses / to escape special characters. For example, if you want to put a space in a file name, you would write it as \space. Please don't ever do this, though. If you put spaces, question marks, and other special characters in file names on Unix, you're likely to confuse the shell and a lot of other tools. Finally, Windows file names and directory names are case insensitive. Upper and lowercase characters mean the same thing. This means that the path name C:, users vlad could be spelled in 1024 different ways. Some people argue that this is more natural. After all, Vlad in all uppercase and Vlad spelled normally refer to the same person, but it does cause some headaches for programmers and can be difficult for people whose first language doesn't use a cased alphabet to understand. The Cygwin package tries to make Windows paths look more like Unix paths by allowing us to refer to the C drive as cygdrive C instead of as C:, although the latter does usually work too. It also allows us to use / instead of / as a separator. But paths are still case insensitive, which means that if you try to copy files called backup.txt in all lowercase and backup.txt with a capital B into the same directory, the second will overwrite the first. To summarize, here are the 3 commands and 2 special directory names that we saw in this episode. In the next episode, we'll see how to create, rename, and delete files and directories. Hello, and welcome to the 3rd episode of the Software Carpentry Lecture on the Unix Shell. In this episode, we'll see how to create, rename, copy, and delete files and directories. As we've seen in previous episodes, one way to interact with a computer is through a command line shell. When we type in commands like these, the shell finds the corresponding programs, runs them on our behalf, and shows us their output. But how do we create files and directories for it to show us? Let's go back to Vlad's home directory, users vlad. As in the previous episode, ls-f shows us the files and directories it contains, with a trailing slash after each directory to help us tell them apart. Let's create a new directory called temp with the command mkdir temp. As you might guess from its name, mkdir means make directory. Since temp is a relative path without a leading slash, the new directory is made below the current one. Let's run ls again. There's our directory. Graphically, we started with this directory tree and created the new directory here. However, there's nothing below it yet. Temp is empty. Alright, we're in users vlad and temp is empty, which we can tell because ls doesn't print any output. If we use ls-a to show directories whose names begin with dot, though, we see that dot and dot dot are there, as they always are. The first name, dot, refers to the directory itself, i.e. users vlad temp. The second, dot dot, refers to its parent, which just happens to be the current working directory users vlad. Let's change our working directory to temp using cd, then run the command nano junk. Nano is a very simple text editor that only a programmer could really love. And we really do mean text. It can only work with plain character data, not tables, images, or any other human-friendly media. This is what Nano looks like when it runs. The cursor is the blinking square in the upper left. It shows us where what we type will be inserted. Let's type in a short quotation, then use Ctrl-O to write our data to disk. By convention, Unix uses the caret, followed by a letter, to mean Control plus that letter. Once our quotation is saved, we can use Ctrl-X to quit the editor and return to the shell. Nano doesn't leave any output on the screen after it exits, but ls now shows us that we have created a file called junk. Running ls with the -s flag shows us how large things are. Unfortunately, by default Unix reports sizes in disk blocks, which probably isn't the least helpful option imaginable. If we add the -h flag, ls uses more human-friendly units for its output. Here, 512 is the number of bytes the file takes up. This is more than we actually typed in because the computer round sizes up. The smallest unit of storage on the disk is typically a block of 512 bytes. Let's tidy up by running rmjunk. rm stands for remove. This command deletes files. It's important to remember that there is no undelete. Unix doesn't move things to a trash bin. It unhooks them from the file system so that their storage space on disk can be recycled. Tools for finding and recovering deleted files do exist, but there's no guarantee they'll work in any particular situation, since the computer may reclaim the file's disk space right away. If we now run ls, its output is empty once again, which tells us that our file is gone. Let's recreate that file, and then move up one directory to users vlad using cd ... If we try to remove the temp directory using rmtemp, we get an error message. rm only works on files, not directories. The right command is rmdir, which stands for remove directory. It doesn't work yet either, though, because the directory we're trying to remove isn't empty. This little safety feature can save you a lot of grief, particularly if you are a bad typist. If we want to get rid of temp, we must first delete the file junk. The directory is now empty, so rmdir deletes it. Let's create that directory and file one more time. Junk isn't a particularly informative name, so let's change the file's name using mv. mv is short for move. We use it to move a file from one place to another. It also works on directories. There is no separate mvdir command. The first argument tells mv what we're moving. The second tells it where the thing we're moving is to go. In this case, we're moving temp junk to temp quotes.txt, which has the same effect as renaming the file. Sure enough, ls shows us that temp now contains one file called quotes.txt. Let's bring that file into the current working directory. Again, we use mv, but this time the second argument is a directory. The effect is to move the file from the directory it was in to a different directory. And sure enough, ls shows us that temp is now empty, but we now have quotes.txt in our current directory. And notice, by the way, that ls with a file name or directory name as an argument lists only that file or directory. The cp command works very much like mv, except it copies a file instead of moving it. We can check that it did the right thing using ls with two paths as arguments. Like many other Unix commands, ls can process up to thousands of paths at once. To prove that we made a copy, Let's delete the quotes.txt file in the current directory and then run ls again. This time, ls tells us that it can't find quotes.txt in the current directory, but it does find the copy in temp, which we didn't delete. Let's make one more copy. This time, though, we don't specify the destination file name, just a directory, so the copy will keep the original's file name. To summarize, here are the commands we've seen so far, along with the two special directory names. In the next episode, we'll see how to operate on text files using pipes and filters. Hello, and welcome to the fourth episode of the Software Carpentry lecture on the Unix Shell. In this episode, we'll look at what makes the shell so powerful, the ease with which it lets you combine existing programs in new ways. As we saw in previous episodes, a shell is a program that takes commands from the user, tells the computer to run the corresponding programs, and shows the user their output. We've already seen commands to move around the file system and to create, rename, copy, and delete files and directories. What we'll see in this episode is that commands like these are much more powerful when they're combined. We'll start with a directory called molecules that contains 6 files describing some simple organic molecules. The .pdb extension indicates that these files are in protein databank format, a simple text format that specifies the type and position of each atom in the molecule. Let's go into that directory with cd and run the command wc star.pdb. The star in star.pdb is a wildcard character. It matches 0 or more characters, so the shell expands the expression star.pdb to be the complete list of .pdb files. The shell does this before wc runs, so the actual command is wc cubane.pdb, ethene.pdb, and so on. wc stands for word count. It counts the number of lines, words, and characters in files. Its output, shown here, prints these values in columns: lines, words, characters, and the file name, 1 line per file, with a line for the total at the end. If we run wc-l instead, our output shows only the number of lines per file. We can use -w to get only the number of words, or -c to get only the number of characters. Now, which of these files is shortest? It's an easy question to answer when there are only 6 files, but what if there were 6,000? That's the kind of job we want a computer to do. Our first step towards a solution is to run the command wc-l star.pdb greater than lengths. Greater than tells the shell to redirect the output to a file instead of printing it to the screen. The shell will create the file if it doesn't exist, or overwrite its contents if it does. Notice that there is no screen output. Everything that wc would have printed has gone into the file lengths instead. ls lengths confirms that the file exists, and we can print its contents to the screen using cat lengths. Cat stands for concatenate. It prints the contents of files one after another. In this case, there's only one file, so cat just shows us what's in it. Now let's use the sort command to sort its contents. This does not change the file. Instead, it prints the sorted lines to the screen, as shown here. We can put the sorted list of lines in another temporary file called sorted lengths by putting greater than sorted lengths after the command, just as we used greater than lengths to put the output of wc into lengths. And now we can run another command called head to get the first few lines in sorted lengths. Giving head the argument -1 tells us that we only want the first line of the file. -20 would get the first 20, and so on. This must be the file with the fewest lines, since sorted lengths hold files and their line counts in order from the least to the most. If you think this is confusing, you're in good company. Even once you understand what wc, sort, and head do, all those intermediate files make it hard to follow what's going on. How can we make it easier to understand? Let's start by getting rid of the sorted lengths file by running the sort and head commands together. That vertical bar between them is called a pipe. It tells the shell that we want to take the output of the command on the left and use it as the input to the command on the right, without explicitly creating a temporary file. The computer can create such a file itself if it wants to, or run the two programs simultaneously and pass data from one to the other through memory without ever putting it on disk. We don't have to know or care. Well, if we don't need to create a temporary file sorted lengths, can we get rid of the lengths file too? The answer is yes. We can use another pipe to send the output of WC directly to sort, which then sends its output to head. This is exactly like a mathematician nesting functions and saying the square of the sine of x times pi. In our case, the calculation is head of sort of word count of star.pdb. This simple idea is why Unix has been so successful. Instead of creating enormous programs that try to do many different things, Unix programmers focus on creating lots of simple tools that each do one job well and work well with each other. 10 such tools can be combined in 100 ways, and that's only looking at pairings. When we start to look at pipes with multiple stages, the possibilities are almost endless. Here's what actually happens behind the scenes when we create a pipe. We'll use an octagon to show a running program. The technical term for this is a process. It's a program that's actually loaded into memory and live. Every process has at least one input channel called standard input. By this point, you may be surprised that the name is so memorable, but don't worry. Most Unix programmers call it stood-in, just to be safe. Every process also has a default output channel called standard output, or stood-out. When we run a program normally, the shell temporarily sends whatever we type on our keyboard to the process's stood-in, and sends whatever the process prints to stood-out to our computer's screen. For example, if we run wc-l star.pdb greater than lengths, the shell starts by telling the computer to create a new process to run the WC program. Since we've provided some file names as arguments, WC reads from them instead of from standard input. And since we've used greater than to redirect output to a file, the shell connects the process's standard output to that file. Here's what happens when we run wc-l star.pdb pipe to sort instead. The shell creates two processes, one for each component of the pipe, so that WC and sort run simultaneously. The standard output of WC is fed directly to the standard input of sort. Since there's no redirection with greater than, sort's output goes to the screen. And if we run wc-l star.pdb pipe to sort, pipe to head -1, we get the three processes shown here with data flowing from the files through WC to sort and from sort through head to the screen. This programming model is called pipes and filters. A filter is a program that transforms a stream of input into a stream of output. Almost all of the standard Unix tools can work this way. Unless told to do otherwise, they read from stood-in, do something to what they've read, and write to stood-out. A pipe is just a connection between two filters. Behind the scenes, the computer may do some clever things to move data around, but from the user's point of view, all a pipe does is move bytes from one process to another. The key is that any program that reads lines of text from standard input and writes lines of text to standard output can work with every other program that behaves this way as well. You can and should write your programs this way so that you and other people can put those programs into pipes to multiply their power. To summarize, we now have a bunch of commands for moving around the file system and 3 for working with text: WC to count things, sort to sort them, and head to select lines from the front of a file. After this episode is over, please go and explore a few other simple text processing commands, such as tail, split, cut, and unique. Remember, each tool you learn multiplies the power of the tools you already know. We've also met 3 more special characters: the pattern matching wildcard star, redirection with greater than, and most important of all, the pipe, which allows us to connect processes together. Again, once this episode is over, please take a moment to find out what 2 other characters do: less than, which redirects input, and question mark, a wildcard that matches a single character instead of any number. In our next episode, we'll have a look at how Unix controls who can do what to files and directories. Hello, and welcome to the 5th episode of the Software Carpentry Lecture on the Unix Shell. In this episode, we'll have a look at the tools Unix gives you to control who has access to what. In the previous episodes in this lecture, we looked at how to use a command shell to interact with a computer and met a few commonly used commands such as pwd, mkdir, and cp. We also met the wildcard character star and saw how to redirect output with greater than and create pipes with pipe. It's now time to look at how Unix determines who can see the contents of which files, and at how it controls who can change those files and run particular programs. We're going to skip over a lot of the details and give a simplified overview. We'll also defer discussion of how Windows manages permissions until the end of the episode. The concepts are similar, but its rules are different, and unfortunately there's no exact mapping between its rules and Unix's. Let's start with a single user. She has a unique username and user ID. Her username is textual, and her user ID is an integer. It might seem redundant to have this as well as her username, but integers are easier for computers to work with. Computers also manage groups. Each group has a unique group name and numeric group ID. The system administrator, or anyone with equally godlike powers, can put a user in any number of groups. The list of who's in what group is usually stored in the file /etc/group. If you're in front of a Unix machine right now, or are using Windows and have Cygwin installed, take a moment and have a look at that file. The third part of the Unix user model is called all. It's everyone else, i.e. everyone who isn't the user we're currently concerned with, or a member of any of the groups we're considering. Now let's look at files, and directories as well, of course. Each file stores the user ID of its owner and the group ID of its owning group as well. This means that every user on the system falls into one of three categories: the owner of the file, someone else who's in that file's group, and everyone who doesn't fit into the first two categories. For each of these three categories, the computer keeps track of whether people in that category can read the file, whether they can write to it, i.e. modify the file, and whether they can execute it, i.e. run it if it's a program. For example, one file's permissions might be on or off as shown in this table. This means that the file's owner can read and write it, but not run it. Other people in the file's owning group can read it, but not modify it, and nobody else can do anything with it at all. Let's have a look at this model in action. If we cd into the labs directory, ls shows us that it contains three things: safety.txt, setup, and waiver.txt. If we run ls-f, it puts a star at the end of setup's name. This is its way of telling us that setup is executable, i.e. that it's a program of some kind that we can run. Now let's run the command ls-l. The -l flag tells ls to give us a long form listing. It's a lot of information, so let's go through the columns in turn. On the right side, we have the files and directories names. Next to them, moving left, are the times they were last modified. Backup systems and other tools use this information in a variety of ways that we'll explore in a later lecture. You can use it right away to tell which files are younger or older than which others. Next to the modification time is the file's size in bytes. Next to that is the ID of the group that owns it and of the user that owns it. We'll skip over the second column for now because it's the column on the left that we care about most. This shows the file's permissions, i.e. who can read, write, or execute it. Let's expand one of those permission strings and have a closer look. The first character tells us what type of thing this is. A dash means it's a regular file, while a D means it's a directory. The next three characters tell us what permissions the file's owner has. Here, the owner can read, write, and execute the file. The middle triplet shows us the group's permissions. If the permission is turned off, we see a dash, so R-X means read and execute, but not write. The final triplet shows us what everyone who isn't the file's owner or in the file's group can do. In this case, it's R-X again, so everyone on the system can look at the file's contents and run it. Before we go any further, let's run ls-a-l to get a long-form listing that includes directory entries that are normally hidden. As you can see, the permissions for dot and dot dot, this directory and its parent, start with a D. But look at the rest of their permissions. The X means that execute is turned on. What does execute mean for a directory? It's not a program. How can we run a directory? In fact, X means something different for directories. It gives someone the right to traverse the directory, but not look at its contents. The distinction is subtle, so let's have a look at an example. Vlad's home directory has 3 subdirectories called Venus, Mars, and Pluto. Each of these has a subdirectory in turn called notes, and those subdirectories contain various files. If a user's permissions on Venus are r-x, then if she tries to see the contents of Venus and Venus/notes using ls, the computer lets her see both. If her permissions on Mars are just r-, then she is allowed to read the contents of both Mars and Mars/notes. But if her permissions on Pluto are only --x, she cannot see what's in the Pluto directory. ls Pluto will tell her she doesn't have permission to view its contents. If she tries to look in Pluto/notes though, the computer will let her do that. She's allowed to go through Pluto, but not look at what's there. This trick gives people a way to make some of their directories visible to the world as a whole without opening up everything else. So much for looking at permissions. If we want to change them, we use the chmod command. The name stands for change mode, which once again isn't particularly memorable. Here's a long-form listing showing the permissions on the final grades in the course Vlad is teaching. Whoops! Everyone in the world can read it. And what's worse, modify it. A crafty student could go in and change his or her grade. They could also try to run the grades file if they wanted, which would almost certainly not work. Here's the command to change the owner's permissions to rw-. The U signals that we're changing the privileges of the user, i.e. the file's owner, and rw is the new set of permissions. A quick ls-l shows us that it worked. Let's run chmod again to give the group read-only permission and then display the results. Notice as we race by that we've put 2 commands on a single line. We can do this as long as we separate them with a semicolon. Finally, let's give all, everyone on the system who isn't the file's owner or in its group, no permissions at all. That's what A equals means. The A signals that we're changing permissions for all, and since there's nothing on the right of the equals, all's new permissions are empty. Those are the basics of permissions on Unix. As we said at the outset though, things work differently on Windows. There, permissions are defined by access control lists, or ACLs. An ACL is a list of pairs, each of which combines a who with a what. For example, you could give the mummy permission to append data to a file without giving him permission to read or delete it, and give Frankenstein permission to delete a file without being able to see what it contains. This is more flexible than the Unix model, but it's also more complex to administer and understand, at least on small systems. If you have a large computer installation, nothing is easy to administer or understand. Some modern variants of Unix actually support ACLs, as well as the older read-write-execute permissions, but hardly anyone uses them. Now that we understand how permissions work, it's time to start creating our own programs. Let's start by running cat greater than smallest. Since we didn't specify an input file, cat will read from the keyboard, i.e. its input will be whatever we type. And since we put greater than smallest at the end of the command, the computer will send cat's output to a file called smallest. Making a long story short, this command will copy whatever we type into a file called smallest. It's like a text editor, but without the most useful bits. Type in this line, wc-l star.pdb, pipe to sort, pipe to head -1. You may remember this as the pipe we constructed in the previous episode to find the smallest molecule file. After pressing enter to end the line, type Ctrl-D. You should immediately get a new shell prompt. Ctrl-D means end of input on Unix. It's how we tell cat, or any other program, that there's nothing more for it coming from the keyboard. The equivalent control character on Windows is Ctrl-Z. Now that our commands are in the file, let's give ourselves the right to run that file as a program by typing chmod u+x smallest. The argument u+x tells chmod to add execute permission for the user without changing anything else. We can use minus to subtract permissions as well if we want. And now let's run smallest by typing in its name just as we would type in the name of any other program. To be sure we're getting exactly the file we just created, we type /smallest to tell the shell that we want the smallest that's in the current working directory. This guarantees that even if there's another program called smallest somewhere else on the computer, the shell will run ours. Sure enough, if we're in the directory containing our PDB files, our little program's output is exactly what we'd get if we ran that pipeline ourselves. Try doing that with a bunch of GUIs on your desktop. Hello, and welcome to the 6th episode of the Software Carpentry Lecture on the Unix Shell. This short episode will show you how to find things in files and how to find files themselves. We're looking at how to interact with a computer using a command line shell. Listening to how people talk about search, you can often guess their age. Just as young people use Google as a verb, crusty old Unix programmers use the word grep. Grep is a contraction of global regular expression print, which was a common sequence of operations in early Unix text editors. What the grep program does is find and print lines in files that match a pattern. Here's the file we'll use for our examples. It contains 3 computer haikus taken from a competition that Salon magazine ran in 1998. Let's run the command grep not haiku.txt. Here, not is the pattern we're searching for. It's a pretty simple pattern. Every alphanumeric character matches against itself. After the pattern comes the name or names of the files we're searching in. As you can see, the output is the 3 lines in the file that contains the letters NOT. Let's try a different pattern, day. This time, the output is lines containing the words yesterday and today, which both have the letters DAY. If we give grep the -w flag, it restricts matches to word boundaries, so that only lines with the word day will be printed, not lines with today or daytime. In this case, there aren't any, so grep's output is empty. Another useful option is -n, which numbers the lines that match. Here, we can see that lines 5, 9, and 10 in the file contain the word it, or a word that contains it. As with other Unix commands, we can combine flags to get only whole word matches with line numbers. Here's another example. -i makes matching case insensitive, while -v inverts the match so that it only prints lines that don't match the pattern. Grep has lots and lots of options. To find out what they are, we can type man grep. Man is the Unix manual command. It prints a description of a command and its options, and, if you're lucky, provides a few examples of how to use it. Grep's real power doesn't come from its options, though. It comes from the fact that its patterns can be regular expressions. That's what the RE in grep stands for. Regular expressions are complex enough that we've devoted an entire lecture to them. If you want to do complex searches, please take a few minutes to watch its first few episodes. One caution: grep's regular expressions use a slightly different syntax than what's used in most programming languages. However, the basic ideas and rules are exactly the same. While grep finds lines in files, the find command finds files themselves. Again, it has a lot of options, too many to cover here. To show how its basic features work, we'll use this directory tree. Under Vlad's home directory is one file, notes.txt, and 3 subdirectories: thesis, which is sadly empty, data, which contains 2 files, first.txt and second.txt, and a tools directory that contains the program's format and stats, and an empty subdirectory called old. Here's a textual representation of that same tree created using the Unix tree command. As with ls-f, trailing slashes show directories, and trailing stars show files we could run as programs. For our first command, let's run find.-type d. Here, dot is the root directory of our search. Find will only look in it and the things it contains. -type d means things that are directories. Sure enough, find's output is the names of the 5 directories in our little tree, including dot, the current working directory. If we change -type d to -type f, we get a listing of all the files instead. Find automatically goes into subdirectories, their subdirectories, and so on to find everything that matches the pattern we've given it. If we don't want to go that deep, we can use -max depth to restrict the depth of search. Here, -max depth 1 tells find to only look at this level, so the only file it finds is /notes.txt. The opposite of -max depth is -min depth, which tells find to only report things that are at or below a certain depth. -min depth 2 therefore finds all the files that are 2 or more levels below us. And here's another option, -empty. This restricts matching to empty files and directories, of which we have 2. We can search by permissions too. Here, for example, we can use -perm -u equals x to find both files and directories for which the user has x permission. Combine this with -type f to exclude directories, and voila, a list of runnable program files. Let's try matching by name with find.-name star.txt. We expect it to find all the text files, but it only prints out /notes.txt. What's gone wrong? Well, if you recall, the shell expands wildcard characters like star before commands run. Since star.txt in the current directory expands to notes.txt, the command we actually ran was find.-name notes.txt. Find did what we asked. We just asked for the wrong thing. Let's try again, but this time we'll put star.txt in single quotes to prevent the shell from expanding the star wildcard. This way, find actually gets the pattern, not the expanded file name notes.txt. Sure enough, this time the output is the names of all 3 text files. As we said in previous episodes, the command line's power lies in combining tools. We've seen how to do that with pipes. Let's look at another technique. As we just saw, find.-name star.txt in quotes gives us a list of all text files in or below the current directory. Here's how to combine that with wc-l to count the lines in all those files. The trick here is to put the find command inside back quotes. This tells the shell to run find and then replace what's in the back quotes with the command's output. This is exactly what the shell does when it expands star, question mark, and other built-in wildcards, but more flexible, since we can use any command we want as our own wildcard. So, when the shell executes this line, the first thing it does is run the command that's inside the back quotes. Its output is the 3 file names datafirst.txt, datasecond.txt, and notes.txt. The shell then replaces the back quotes with that output to construct the command wc-l datafirst.txt, datasecond.txt, and notes.txt. And as you can see, that does what we originally wanted. It's very common to use find and grep together. The first finds files that match a pattern. The second looks for lines inside those files. Here, for example, we can find PDB files that contain iron atoms by looking for the string Fe in all the PDB files below the current directory. If you've forgotten your high school chemistry, Fe is the atomic symbol for iron. So far, we have focused exclusively on finding things in text files. What if your data isn't text? What if we have images, databases, spreadsheets, or some other format? There are basically 3 options. The first is to extend tools like grep to handle those formats. This hasn't happened and probably won't because there are too many formats to support. The second option is to convert the data to text or extract the texty bits from the data. This is probably the most common approach since it only requires people to build one tool per data format to extract information. On the positive side, this makes simple things easy to do. On the negative side, complex things are usually impossible. For example, it's easy enough to write a program that will extract X and Y dimensions from image files for grep to play with. But how would you write something to find values in a spreadsheet whose cells contain formulas? The third choice is to recognize that the shell and text processing have their limits, and to use a programming language such as Python instead. When the time comes to do this, don't be too hard on the shell. Many programming languages, Python included, have borrowed a lot of ideas from it. and imitation is also the sincerest form of praise. Hello, and welcome to the 7th episode of a longer than expected software carpentry lecture on the Unix shell. This episode will take a quick look at job control, a topic that's less important today than it was back in the Dark Ages, but which is coming back into its own as more people begin to leverage the power of computer networks. We're looking at how to control a computer using a command line shell. We've seen how to use pipes to combine programs, which tells the shell to use the output of one as the input of the next. What we'll look at in this episode is how to control programs once they're running. What we really mean by that is how to control processes. A process is just a running program. Some of the processes on your computer are yours. They're running programs you explicitly asked for, like your web browser. Many others belong to the operating system that manages your computer for you, or, if you're on a shared machine, to other users. You can use the ps command to list them, just as you use ls to list files and directories. Here's some typical ps output. Every process has a unique process ID. Remember, this is a property of the process, not of the program that process is executing. If you are running 3 instances of your browser at once, each will have its own process ID. The second column in this listing shows the ID of each process's parent. Every process on a computer is spawned by another, which is its parent, except of course for the boot process that runs automatically when the computer starts up. The third column is the ID of the process group this process belongs to. We won't discuss process groups in this lecture, but they're often used to manage sets of related processes. Column 4 shows the ID of the terminal this process is running in. Once upon a time, this really would have been a terminal connected to a central time-shared computer. It isn't as important these days, except that if a process is a system service, such as a network monitor, PS will display a question mark for its terminal, since it doesn't actually have one. Column 5 is more interesting. It's the user ID of the user this process is being run by. This is the user ID the computer uses when checking permissions. The process is allowed to access exactly the same things as the user, no more, no less. Finally, column 6 shows when the process started running, and column 7 shows what program the process is executing. Your version of PS may show more or fewer columns, or may show them in a different order, but the same information is generally available everywhere. The shell provides several commands for stopping, pausing, and resuming processes. To see them in action, let's run our analyze program on our latest data files. After a few minutes go by, we realize that this is going to take a while to finish. Being impatient, we kill the process by typing Ctrl-C. This stops the currently executing program right away. Any results it has calculated, but not written to disk, are lost. Let's run that same command again, with an ampersand at the end of the line, to tell the shell we want it to run in the background. When we do this, the shell launches the program as before. Instead of leaving our keyboard and screen connected to the program's standard input and output, though, the shell hangs on to them. This means the shell can give us a fresh command prompt and start running other commands right away. Here, for example, we're checking for new Facebook events. Since there's nothing going on, let's run the jobs command. This tells us what processes are currently running in the background. Since we can't think of any other way to procrastinate, we use the foreground command FG. This brings our background job into the foreground. If we have several jobs running in the background, we can control which one we bring to the foreground using FG%1, FG%2, and so on. The IDs are not the process IDs, instead they are the job IDs displayed by the jobs command. Finally, when analyze finishes running, the shell gives us a fresh prompt as usual. The shell gives us one more tool for job control. If a process is already running in the foreground, Ctrl-Z will pause it and return control to the shell. We can then use FG to resume it in the foreground, or BG to resume it as a background job. For example, let's run analyze again and then type Ctrl-Z. The shell immediately tells us that our program has been stopped and gives us its job number. If we type BG%1, the shell starts the process running again, but in the background. We can check that it's running using jobs, and if we want, kill it while it's still in the background using kill and the job number. This has the same effect as bringing it to the foreground and then typing Control-C. Job control was important when users only had one terminal window at a time. It's less important now. If we want to run another program, it's easy enough to open another window and run it there. However, these ideas and tools are making a comeback, as they're often the easiest way to run and control programs on remote computers elsewhere in the network. A future episode will take a look at how we can do that securely. First, though, we need to look at shell variables. Hello, and welcome to episode number 8 of the Software Carpentry lecture on the Unix shell. In this episode, we'll have a look at shell variables. As you've heard several times by now, we're looking at how to interact with a computer using a command line shell. The shell is just a program, and like other programs, it has variables. Those variables control its execution, and by changing their values, you can change how the shell and other programs behave. Let's start by running the command set and looking at some of the variables in a typical shell session. As you can see, there are quite a few, in fact 4 or 5 times more than what's shown on this slide. Using set to show things might seem a little strange, even for Unix, but if you don't give it any arguments, it might as well show you things you could set. Every variable has a name. By convention, variables that are always present are given uppercase names. All shell variables' values are strings. It's up to programs to convert these strings to other types when necessary. For example, if a program wanted to find out how many processors the computer had, it would convert the number of processors variable from a string to an integer. Some variables store lists of values. Here, the convention is to use a colon as a separator. If a program wants the individual elements of such a list, it's the program's responsibility to split the variable's string value into pieces. Let's have a closer look at one of the most important of those list-valued variables, path. Its value defines the shell's search path, i.e., the directories that the shell looks in for runnable programs. If you recall from a couple of episodes ago, if we type a command like /analyze with a specific directory in the path, the shell runs the program that path specifies. Similarly, if we type /bin/analyze, the program runs that specific program. We've provided a specific path so it knows what to do. But what should the shell do if we just type analyze? There are at least 2 things it could run. How should it choose? Its rule is simple. The shell checks each directory in the path variable in turn, looking for a program with the requested name in that directory. As soon as it finds a match, it stops searching and runs the program. To show how this works, here are the components of path broken out 1 per line. On our computer, there are actually 3 programs called analyze in 3 different directories. Since the shell searches the directories in order, it finds the one in /bin, not either of the others. Notice that it will never find the program users_vlad_analyze, since the directory users_vlad isn't in our path. Before we explore variables any further, let's introduce one more command, echo. All it does is print out its arguments. This doesn't sound very exciting, but we can use it to show variables' values. First, let's make sure it works. Yep, echo hello Transylvania puts hello Transylvania as promised. Now let's try to show the value of the variable home with echo home. Whoops, that just prints home. Let's try this instead, echo $home. The $sign tells the shell to replace the variable's name with its value. This works just like wildcards. The shell does the expansion before running the program we've asked for. Thanks to this expansion, what we actually run is echo home Vlad, which shows us the variable's value. Creating a variable is easy. Just assign a value to a name using equals. Changing a value is equally easy. Just assign a new one. Here, we set our secret identity to be Dracula, check it, change it to Camila, and check again. It's important to note, though, that assignment only changes a variable's value in the current shell, not in any other shells that are currently running, or in any shells that are started later. Let's go back and set our secret identity once again. Once it's set, let's run a fresh copy of the shell by typing the command bash. We now have two copies of the shell running, the original, shown in green, and its child, shown in orange. If we echo $secret identity in the child shell, nothing is printed because the variable doesn't have a value. If we exit the child shell and return to the original, we can see that yes, the variable does exist. If we really want the shell to pass a variable to the processes it creates, we must use the export command. Let's try the secret identity example again. After giving secret identity a value, we give the shell the command export secret identity. Note, by the way, that it's not export $secret identity with a $sign. If we typed that, the shell would expand secret identity, and our export command would actually be export Dracula, which would do nothing because there's no variable called Dracula. Now let's run a new shell and type echo $secret identity. Yep, there's our variable. And of course, exiting brings us back to our original shell. If we want to set some variables values automatically every time we run a shell, we can put the command to do this in a file called .bashrc in our home directory. The dot character at the front prevents ls from listing this file unless we specifically ask it to with -a. We normally don't want to worry about it. And the rc at the end is an abbreviation for run control, which meant something really important decades ago and is now just a convention everyone follows without understanding why. For example, here are two lines in Vlad's .bashrc file. These two lines create the variables secret identity and backup dir, give them values, and export them so that any programs the shell runs can see them as well. And while we're here, it's also common to use the alias command to create shortcuts for things we frequently type. For example, we can define the alias backup to run /bin/zarbl with these arguments. Notice that these arguments include references to some variables, so that if we want to change where we put our backups, we only have to change one variable's value in one place. As you can see, aliases can save us a lot of typing and a lot of typing mistakes. In our next episode, we'll have a look at how to connect to other machines securely.
In modern operating systems, the command line allows the user a powerful way to accomplish a diverse set of tasks on the user's computer. In this episode, we'll see how remote logins can be used to connect to other computers and perform command line tasks on the other computers, all without distance being an issue. First, let's start by looking at what happens when we use our desktop computer. When we type information to our computer, for example, a shell command, the text, the ones and zeros that represent each character, is sent from the keyboard to the shell. The shell then displays characters on the screen to represent what we type. If what we type represents a command, the shell will execute the command and additionally display characters representing the output. When we log in to our desktop computer, we type our username and password at the keyboard, which sends it to the shell. The shell passes the login information to the OS, and if the OS authenticates our login information, the shell will give us a command line prompt to interact with the OS. The shell will send the ones and zeros to the screen to represent the characters that make up that prompt. Let's say we want to log in to another computer from our desktop. Let's call this a remote login, and the other computer is a remote computer. A remote login appears nearly the same to the user. However, the username and password information is being passed on to a shell on the remote computer's OS, so it has a longer distance to travel. The shell on the remote computer interacts with its OS and responds back with output, and the output travels back to us. The interaction with the remote computer will be the same as if we had traveled that distance and were typing at the keyboard of the remote computer. In order to invoke a remote login, all we need to know is the secure shell command ssh and the simple syntax ssh username @computer name, and we get prompted for our username and password on the remote computer. Voila! Wrong password? No access, just as we expect. After we log in to the remote computer, we can use the remote shell to use the remote computer's files and directories. When we type exit, we terminate the remote shell and return to our previous shell. Suppose there is a file that we want to transfer from the remote computer to our computer. Now that you know how to run Secure Shell, you can understand what Secure Copy might do. Secure Copy allows you to copy files to or from a remote computer, and it takes advantage of the remote connection setup used by Secure Shell. The syntax is simple and is similar to that of CP and SSH. To copy a file, we first specify the source location of the file that we are copying, followed by the destination directory to where we are copying the file. When specifying the source and destination, we write the username, @, the name of the computer, colon, then the path of the file or directory. If either the source or destination is on a remote computer, then we have to type the password for the user accounts that are being used to make the connection. Secure Copy may also give us feedback on the progress of our transfer. Copying a folder is similar to using the copy command cp in that the -r option indicates we are copying a directory and its contents. If either the source or destination is the current computer, we can omit the user @computer : part. Sometimes we only want to log in to a remote computer to find out or create a piece of information and then return. If this is quick or repetitive, this can get tedious. For example, I need to know how much free disk space there is, and I need to collect this information every hour and keep this information on my personal computer. I could log in, run df-h, save the output as a file, log out, and then SCP, or secure copy, the file from the remote computer to my computer. But the SSH command allows us to pass data streams to a remote command and receive input streams from a remote command. When we provide the command that SSH needs to run remotely, any output that the command generates is sent back to our shell. The remote command is specified as an argument to the SSH command that follows the username and remote computer information. Now we can save the remote command's output to a file. This simplifies the task considerably and still achieves the same result. We have the remote computer's disk usage statistics saved on our computer. Remember that SSH can accept streams of data and pass those to the remote command too. This command sends a stream of characters to a remote shell session. As mentioned before, the remote shell will execute any command on the remote computer that was provided as an argument to SSH. The remote shell session also passes any input it receives to the provided command. In this example's remote command, cat is a command that will receive the input and repeat it entirely as output, and then the rest of the remote command will redirect that output to a file. The command has created a file on the remote computer in the user's home directory that contains the original stream of characters. And we can copy that file from the remote computer to our computer if we like. Why do we call the command used to log into a shell on a remote computer Secure Shell? Until a few years ago, we used to create remote logins by passing our information straight through to the remote computer. However, if a person could intercept our messages to the remote computer and were devious, that person could read our username and password and use them to impersonate us. Not secure, and we don't expect to be impersonated. What we needed was a way to do this without the risk of our passwords and information being stolen. Imagine the information we send as messages that can be protected by locking them. One way to arrange a locking scheme is to have all users connecting to a remote computer use the same lock and key when sending their messages. As we might imagine, this is not safe with many users. If multiple users have copies of the same key, the potential for a single key to get stolen or fall into the hands of a thief is higher. What we really needed, then, was a way to create a lock and key design with two keys, where the message can be locked by one key and only unlocked by the other key. Imagine the remote computer having a set of two keys, and handing out the first and keeping the second. The user locks all of his or her messages with the first key, but only the second key can open it, which only the remote computer has. Anyone pretending to be the remote computer does not have the second key and cannot break the lock. All subsequent messages from the user to that particular remote computer will be done with the remote computer's first key that the user received. And the remote computer continues to use the second key it kept to unlock the messages. This key lock mechanism is called public key encryption, and public key encryption is a standard feature of Secure Shell. In public key encryption, the first key, which is sent out to the user, is the public key. It's okay to send this out to every user, since no one has the second key in the set, called the private key. The locking mechanism is an encryption algorithm, and the public key is used to encrypt our messages to the remote computer. Due to the way these encryption algorithms are designed, the remote computer can use its private key to decrypt the messages, but no other key will work. In order for the remote computer to send messages to us, the same process happens in reverse. We generate a public and private key pair, give the remote computer our public key, the remote computer encrypts messages to us using our public key, and we decrypt the remote computer's messages using our private key. Anyone trying to pose as us will not have the remote computer's private key, and will not be able to understand our message encrypted with the remote computer's public key. This makes it safe to put our username and password and any other sensitive information in our messages. Similarly, in the reverse direction, from the remote computer to our computer, anyone posing as us will not have our private key and cannot decrypt the messages sent from the remote computer using our public key. Also note, users who log in to a remote computer for the first time need to first receive the remote computer's public key and agree to its authenticity. The public key is sometimes represented in a fingerprint format for easier verification purposes. Let's return to the example of saving a log of free disk space every hour. We can imagine putting this inside a loop that repeats every hour. But there's one thing that's still tedious. We have to type our password every single time, every single hour. And the remote computer will probably only wait for a short while for the password before assuming you're not there and giving up. We need to make this process fully automatic. The equivalent of this in the GUI world is the Save Password option, but our way will be more secure. What we want is a way to do silent authentication. We want the remote computer to recognize our username and password in some form without having to type our password interactively. In order to silently authenticate into a remote computer, we need to take advantage of SSH allowing user keys. User keys are user-specific, user-generated, public-private keys. Each user has his or her own user key pair, and it is separate from the host key pair belonging to the user's computer. The host key pair is shared by all users of the computer, and it is used by default when the user key pair is not used. The user keys allow us to embed our password into our user key pair when generating them, making it much harder to fake than the host key pair we use by default, and thus more secure. We use SSH keygen to generate the user key pair. We then have to manually send our user public key to all the remote computers that we want to use it. If we don't send our user public key to a remote computer, then when we log into that computer, by default, we will have to use the host public-private key pair for encryption, and we also have to authenticate with our username and password on the remote computer. When using SSH to log into a remote computer that has our user public key, we type in our password so that it matches the password we embedded in our user key pair. The trick to silent logins is to generate a new user key pair and provide an empty password as the key pair password when prompted by pressing Enter. We copy this particular public key to every remote computer for which we want silent login. Here are 3 different ways to copy the user public key to the remote computer so that it can be found. We can now start writing scripts that run commands, send input to remote computers, or receive output from remote computers in a secure way. All of this can happen silently without us typing our password. Thank you for listening.